All right, so today we're going to continue talking about where we left off last time, which was the numeration systems. We'd actually gone through all of the numeration systems that we're going to look at. We had finished with the Roman numerals, and I left you with a task to find out, if you could, what was wrong with the clock on Rayleigh Chapel. So, for those of you whom I'm asking this to for the first time, because a few of you have had me ask you this before, did you check, and do you know what's wrong with the clock on Rayleigh Chapel? Some nods. So I'm going to ask Hannah, because Hannah, I know, has not had me before. So, Hannah, what's wrong with the clock on Rayleigh Chapel?
The 4 is 4 eyes instead of IV.
That's right. The clock on Rayleigh Chapel has the number 4 on there written as 4 eyes instead of an IV. So I was actually presented with that task by Dr. Whitlock when I first came on campus. Have you looked at Rayleigh Chapel? What's wrong with it? So there you go. There actually is an error on the clock on Rayleigh Chapel. But what we're going to move on to next is actually something a little bit different. And we're going to talk about base 10 blocks. Have you seen base 10 blocks before? They're used very often in elementary school, and I have a whole slew of them. I'm going to send them around so you can kind of take a picture of them. I'll draw the pictures for you on the board in a moment, but there are different little pieces in here. And I even have, some others. So the first thing that you have when you're working with base 10 blocks, you have little bitty ones, okay? These are the units, so they're just little bitty squares, okay? And then if you stick 10 little bitty squares together, it turns into one long rectangle. And this is called a long. All right, so these are 10 and 1, 10 all stuck together. Again, like I said, I'll pass them around in a moment. If you stick 10 of the longs together, you get what looks sort of like a square. I mean, it's got dimension to it, right? Because it's got the height, but visually from the front it looks like a square. And this has a value of 100 because it's 10 times 10 of the little blocks, right? So we've got 100 little blocks here. And then if you stick, what do I have with me? I don't. If you stick 10 of these blocks together, so imagine, since I don't have the actual one to do it with, I think this is 10 of them. Imagine these all stacked up and stuck together so that they're not, shifting around my hand. This is called a block. Okay? So a block is actually how many of the little cubes units? It's 1,000. Okay? So this is a visual imagery of these kinds of ideas. And let me send this one around. I'll show you here's one. I'll draw pictures to you here in a minute. But I want to also show you that there's nothing special about 10 except that we use it the most. All right? You can do base blocks in any number system. So this right here, inside here, and I do actually have all my pieces here. These are base 3 blocks. So I still have the unit. It's a little square, right? The little bitty one looks just like the unit in the red box that I just sent around. But then if I stick 3 of them together instead of 10, it makes a long. Okay? So this is a long in base 3. There's just 3 of them stuck together. If you stick 3 of the longs together, it will turn into that same square shape that we had before, right? So how many do we actually have when we're talking about this particular shape in base 3? There's actually 9 of these, aren't there? There's not 100 like there were in base 10, okay? And then if I stick 3 of the flats together, I get a block. How many is in this little block? There are 27. So we can actually see that this works for any base system, which is really good because we're about to look at some other base systems. All right, so let me draw our units, or our base 10 blocks on the board for us. So the unit looks like a small square, right? Little bitty one. A long actually looks like one long rectangle. You do not need to draw all the individual units in there unless it asks you something specific about that. A long, this is what it looks like. A flat better look different than a unit, okay? So there better be a clear distinction that the flat is much larger than the unit size, because they're both squares, agreed? Okay, so you have to make sure that your unit and your block do not, or your unit and your flat don't really look alike. And then the last one, the block, needs to look like it has 3 dimensions to it because it is 3-dimensional. So hopefully you remember back from when you were younger how to 3-dimensionalize a square into a block that looks like this. So I'm not going to spend too much detail on this, but they're going to ask you to draw some pictures. So you're going to be given, let me do one example. I don't have it written on here, but we'll do it on the board. If you were asked to draw the number 243 in base 10 representation, what would you need? Let's start with the 2. What would I draw 2 of? 2 flats. So I need 2 rather large squares. Okay? Then what do I need? 4 longs. And they better look just as long as those squares are long, right? Because they should be. This is a terrible picture. Pretend like mine look better. There's 4 longs. And then what do I need? 3 units. Okay, so 3 of the small squares at the end. So some variation of that, or something looks something like that, would be the number 243 if you were drawing it with base 10 representation with the blocks. Any questions on that? Okay. So this is sort of leading us into this idea of other base systems and other number systems. And undoubtedly, I always have somebody say, but I mean, I don't know where they would actually teach this in the other kids. Well, part of what we're going to be doing working with the other number systems is to put you in a position where you feel a little bit uncomfortable. You're not very comfortable working in base 3 or base 7 because that's not the number system you're most familiar with, right? Right, if I ask you to add something inside of base 7, probably you're going to make some mistakes because you're not familiar and comfortable with base 7. So think for yourself here at the moment, what happens when your students come in and you first start talking about addition and subtraction in base 10? Well, they're familiar with the numbers, but they're not familiar with how it works in base 10 because they've not done it before. Does that make sense? So part of this process in this particular section is putting you a little bit outside your comfort zone to help you identify with your students for when they first see addition and subtraction and whatnot for the first time. So we're going to come back to this number system issue in later chapters as well, so that we can put ourselves maybe in a little bit in the position of how uncomfortable it feels the first time you do it in another system, because that's what your students are feeling. All right? So let's talk first about some of the number systems to give ourselves some background to be able to work with. So in base 3, well, let's talk about base 10. I didn't write it on here, but in base 10, how many numerals do we have? 10 numerals. I think we did that last time. We start with the number 0 and we end with the number 9. Okay, so we have 10 numerals, but 10 is not a numeral, right? Okay, it's actually a 2-digit. It's 2 numerals in 1. So in base 3, how many numerals do you suppose we're going to have? We are going to have 3, but we're not going to have the number 3. We're going to have 0, 1, and 2, right, Katie? So 0, 1, and 2. Still 3 numerals, but we stop short of the actual number that we call the number 3. Just like in base 10, we don't have a numeral for the number 10. Right? So what do you think base 7 is going to be? 0 through 6. Good. Base 12 is a little different, because what's different about 12 than about the 7 and the 3? I got to go past my digits that I have, right? It's actually more than my base 10. I have more numerals. So I should still have 12 numerals, right? But if I write the numbers from 0 to 9, that gives me the first 10. So that's where we're going to start. We're going to go from 0 to 9. And then we're going to deviate a little bit from those of you who've been in contemporary math. In contemporary math, we need 2 more numerals. Do you remember what they were? They were A and B. This book doesn't use A and B. They use T for 10 and E for 11, and if you got 12, they would use a W. Okay? So we're going to go with what they've got. This is T and then E. So T is the number 10. Okay, single numeral, it's got to be a single numeral to be able to be used. And then E is the number 11, and of course there is no 12 in base 12. Okay? So we're going to do like we did with the other numeration systems. The first thing we're going to do is find the numeral before and the numeral after the one we're working on. And these particular numerals were chosen for a reason. They were chosen because, and this happened when we were doing the other numeration systems as well, one of the numbers, either the before or the after, is very simple and straightforward to find. It works just like it does in base 10. The other one won't. Okay? So I want you to understand that sometimes it works the way that it worked before, and other times you've got something else going on. So let's take the number 14, base 5, and we're not going to read it as 14, because 14 means that I've got something in base 10. That's why we put the teen on the end. So we're going to read it as 14, base 5. So in 14, base 5, what's the number that is preceding, that is comes before 14? It would be 13. Okay, so just like our number system, nothing different at all, right? Okay, so that looks good. No problems there. Now, the number afterward is different. So my succeeding term, well, in our system, what would come after 1, 4? 1, 5. Why is that not okay in this system? There's no 5 in base 5, right? We've run out. So picture it like this. You have $1 bills and you have $5 bills. No other dollar bills exist. Everybody with me? Okay. So when you're getting change for something, or when you're making, when you're working with money, we tend to like to have as few bills as possible. This is just what we do, right? So if somebody wanted to give you 1, 5, which is the number we're looking at, this would be the equivalent of 1 $5 bill and 5 $1 bills. Well, that would be a little awkward, wouldn't it? Unless you just didn't have the change in the cash register drawer, nobody would give you your change back like that. What would they do instead? Remember, we only have 1s and 5s, so don't go adding the $10 bills in the mix here. How much is 5 1s and 1 5 worth? It's worth the same as 2 5s would be, isn't it? So this would actually be the number 2, 0, base 5. This would be the equivalent of having 2 5s and 0 1s. Okay, once you get to 5 1s, and we do this with our money, you don't give people back 5 1s unless you just don't have 5s, right? You give them back a $5 bill. So this is equivalent to giving back the additional $5 bill. Another way you can think about it is like this. In our number system, when we run out of digits, we run out of digits when we hit the number 9, right? So if we ran out of the digits, we'd have the number 1, 9. What comes after 1, 9? 2, 0, 20. The same thing happens when you run out of digits in any other number system. When you run out of digits, you actually write down the number 1 greater in the place before, and you turn the last digit into a 0. Don't you? So it's the same thing. All right, let's do this next one. This one looks odd because it's in base 12 and I've got a letter involved, right? So let's first remember what this T means. What does T mean to have it here in base 10? Or sorry, in base 12? This is the number 10. So just jot that down for yourself. Pause for a moment. Okay, so just to let you know what I'm doing, this is calibrating the board because my pen is not actually writing where I'm touching. Okay. All right, so do you have any idea which of the numbers is the most natural one to find, the before or the after on this one? The after one is, yeah, the successive term, the succeeding term. What number would come after T00? T01, just like with us. If this T had been any other number, we would just add the number 1 to the end. So we'll do the same thing here. This is T01, base 12. Make sure that when you're working in another base, you put that base as a subscript, written out as a word. The easiest way to keep the complications at a minimum. Because if you don't write anything, it's assumed you're working at base 10. That's our default. All right, so what do we do in our base system when we have a number that ends in 0, 0? So let's pretend this is our system. Instead of it being a T, it's an 8. Okay, so think with me. What do we do? What comes before 8, 0, 0 in base 10? 799, right? So if I'm writing them in order, 799 comes before here. All right. So the first digit, the one that wasn't a 0, turned into one number less, correct? And then the other 2 digits turned into the largest digit in our number system. Did everybody follow that? So the zeros right here, by comparison, became the largest digit that we have. It went from being the smallest digit to the largest digit. And the number at the beginning simply became 1 less than we had previously. So let's try that with the number T00. The T needs to become 1 less than it was originally. So what's 1 less than T? It is 9, because T is worth 10. So this is the preceding number. 1 less is a 9. The numbers at the end are supposed to become the largest number in that base system, which would be E in base 10, or 12, yes. So they both become E's. And I write the subscript of 12.
repeat the EE thing?
Yes. In our number system, the 2 zeros at the end, right, they become the largest digit that we actually have in our system. They become 9s, because 9's our largest digit. But in base 12, the largest digit is an E. So they became E's for the same reason ours became 9's. Yes, Nicole?
I don't understand. I thought in base 12 just a T was 10. So why is it T00 is 10?
T00 is not 10. This is the number 10, and this is the number 0, this is the number 0. We've got a 3-digit number.
I thought you meant you were playing the whole thing as that
No.
meant 10.
No, just the T. I was isolating the T at the beginning because that's the one that's a little off.
Okay. So it would be like 100. It would be like, yeah.
Well, we're going to get there in a second about what it actually is,
Okay.
this number actually is. But yes, it would be something much larger than 10. All right. So what we're going to do now is do exactly what you're sort of asking is, okay, well, how big is that number? We're going to be working between our number system and whatever other number system, whatever base system we want to go to. And we're going to convert back and forth, okay? So we can convert one direction and we can convert back the other direction. And so that's what we're looking at. The first one is we're converting some other base into our base 10. Okay, so we're converting something else. So it would be kind of like the ones in the last slide. If I took the 1,4 base 5 or the T00 base 12, I'm going to take a number like that, something that's not in base 10, and I'm going to put it into base 10. Okay? So taking a look at these, the one we're going to work with, in fact, you even see the T00 base 12 down there. The first one we're going to actually work with is 1011 base 2. Now, I bring up base 2 just for the moment because I want you to understand that you're not comfortable perhaps working in base 2, but base 2 is used in real life. There are a few number systems that are. Do you know what base 2 is used for in real life? Yeah. Binary, and what is it? It's for computers. So binary is used in computer programming. There's another base system that's used in computer programming. Does anybody know? It's called hexadecimal. It's base 16. Okay, so that's another system that is used in computers. There's another one that you're familiar with. We don't use it with the numerals kind of the way it is, but you're familiar with the base 12 number system. You just realized it until today. Do you know what the base 12 number system is that you're familiar with? The clock, the time, right? We do our clocks in base 12. I know, we've got the 10 and the 11 and the 12 written on there, so the symbols don't really match what we're talking about here, but we use it the same way. Okay? So there are other number systems that we use, and when we deal with money, it's not really a clean base 5, but we do have that sort of a feel to it, right? Because we don't give 5 ones back. We don't give 9 ones back. We do things in terms of 5s or in terms of 10s, depending on the bills that we're working with, 20s too. All right, so let's take a look at how this works. What we do is we take the numeral that we're given, and we put it in expanded form. Okay, so we saw expanded form before. Expanded form means taking a look at each of the individual numerals and figuring out what their place value is that they have. In our system, we have the ones place, we have the tens place, we have the hundreds place, we have the thousands place, and so forth, right? They're all powers of 10. But they're powers of 10 because it's in base 10. So if I'm in base 2, what do you suppose my powers are going to be? 2. Powers of 2. So we're going to take a look at these. I'm going to spread them out a little bit so that we can see them a little more clearly. This is the ones place, or the 2 to the zeros place, if you prefer. And then this is the 2's place, or 2 to the 1. And then what happens after this in our system is we'd use the number 100. We use it because it's 10 squared. So we're going to use 2 squared here, and then 2 cubed here. So what is 2 squared? So everybody's on the same track. 4. And 2 to the third is 8. Okay, so those are the numbers we have. So what we're actually going to do is we're going to multiply out the expanded form. What does that look like? Well, that means that I'm going to take the number that's in that place value, which is the 1, times the place value. So I've got 1 times 2 cubed. And then I'm going to take the number that's in the place value next, which is a 0. I'm going to write it just so that we see it. I recognize it's still not worth anything, but 0 times the 2 squared. And then I've got the 1 times the 2, back in the 2's place. And then in my 1's place, I have 1 times 1. Now, with binary, it's really easy to multiply these out because you either have it or you don't. There's really not any multiplication for real to do. We already did this one. This is 8. This is multiplication by 0, so it's nothing. 2 times 1's 2, and then I've got 1. So what number is this in our number system? So we said it. 11, right? This is the number 11. If you want to sort of distinguish this in your mind, you could write base 10 next to it just to sort of clarify to you that you really are finished in the right base. But if you don't write it, it's understood to be base 10. Okay. 2. We started in binary base 2. And that's the reason over here, Katrina, that we were doing these down here, the base 2, the powers of 2.
So you said we write down lowercase 10?
If you want, you can write this like this. Either one is fine. If you don't write it, it's fine too. But yeah. All right, let's do the next one because it's one we actually already saw earlier. T00 base 12. I got some zeros, so that's friendly. But let me write the expanded form so we can see what's happening. We have a 3-digit number. We've got the 1's place. This is base 12, so I've got the 12's place. What comes next? 12 squared. And do you guys remember what 12 squared is? That's 144. Okay, so we're going to need that in a moment, but that is 144. Now, this says T00, but we've already established that T actually means 10. Okay, so T is the number in our system that we call 10. Okay, so we're going to do just like we did in the previous problem. We're going to multiply each value times the place value that it's in. This is 10 144s, or 12 squareds. Plus, and again, like I'm right, I recognize that they're not worth anything, but 0 times 12, and then 0 times 1. So what is 10 times 144? You do not need your calculators for this. I know you can do it. Thank you. Good. 1,440. And again, if you want to write the 10 down there next to it, like Kristen asked about, you can write there the whole subscript 10 if you'd like. So this is actually bigger than 1,000, right, Nicole? All right, let's take a look at the other direction then, because the other direction is the one that leads itself to being a little bit more complicated. All right, so now we're turning our number into another base system, okay? So this is sort of what I want you to picture in your mind as you're doing it. We're going to go through the calculation to do it, but I want you to picture in your mind what's happening. What's happening is I brought in a box, and you guys have seen it before because you're education majors, so you know they exist. A box of all the little lonely crayons and outside of the crayon box. You guys know what I'm talking about, right? Because they happen, right? They always happen. So you've got a whole box, and kind of like I had the box of the manipulatives back there, right? A big old box of crayons, and I dump them on the floor. Okay? In my box, there are 11,028 crayons. That'd be a lot. But pretend. Okay, we've got this huge number of crayons on the floor. And for whatever reason, we're wanting to bag them up into Ziploc baggies or whatever in a certain way. We're going to bag them up based on base 4. So that means I've either got a single crayon, I've got a bag of 4 crayons, or a bag of 4 squared, which is 16 crayons, or whatever. Okay? So my goal is to use up as few baggies as possible, which means I want the most in the bags as I can get. Okay, can you imagine what I'm doing here? Okay, so I'm going to show you how this works. So what we've got to do, we first got to figure out what's the biggest number of crayons using this base 4 idea that we can put into a bag. So I've already done the first ones. I've got the number 1, I've got the number 4, and then we had 4 squared. And I'll write the actual value underneath so that we're seeing it in both directions, which is 16. What will come before the 4 squared? What's next? What's my next power? 4 cubed. Do you know what 4 cubed is? That is 64. So I'm still nowhere near 11,000. What's next? 4 to the 4th, which is what? 256. I'm getting closer. Next power is 4 to the 5th, which is what? 4,024. I'm sorry, 1,024. Hey, I'm bigger than 1,000 now. How about 4 to the 6th? 4,096. And I'm going to show you one more, though we're not going to need it, and you'll see why. What is 4 to the 7th?
16,384.
And how do I know I don't need that one? That is bigger than the 11,000 crayons that I have. Okay? Everybody with me? So this is what you first have to do. You have to figure out what's the most number of crayons you can put in a baggie under this sort of a condition. And the most is 4,096 crayons. Okay? So what we're going to do next is we're going to do a really, really cool algorithm on how to figure out how many, and there's more than one way to do this, but this is one that your book presents, which is really very friendly on how to do this. We're going to do what looks like a little bit like division at first. What we want to do is we want to take that 11,028, and what we really want to do is we want to divide it by 4096. That will tell us how many bags that we can get of size 4096. But because I'm going to continue this in a moment, I'm going to draw this a little bit differently, and our answer is going to look a little bit differently. So the first thing you do is you're going to grab your calculator. So you get to use your calculator on this. I don't need to see the actual division step. Isn't that fabulous? And I want you to tell me how many times will 4096 go evenly, that is the whole number part, into 11,028. Twice. It will go in twice. So we're going to put the number 2 here on the right. Okay. The next thing we're going to do is we're going to take that number 2 and we're going to multiply by that number 4096, and you're going to tell me what you get.
8,192.
Awesome. And then just as with any kind of division, when you do the next step, you subtract, right? So what do you get when you subtract? Thank you. We multiply this 2 by this 4096. Okay, is everybody to this point okay? Okay, the next thing we do is we go straight down the line. We did the 4096, now we're going to do 1024. Okay, so the 1024 goes on the outside. And we're going to repeat that. We're looking at the division. How many times will 1024 go into 2836? It is 2. And what is 2 times 1024? 2048. And then we subtract. 788. Okay, so mine, well, I'll hang on to it. Yours is still there. We did the 4096 and the 1024. What was the next value after the 1024? 256. So we're going to write that next. How many times will 256 go into 788?
3.
Will it go in 3?
Yeah.
Excellent. All right, what is 3 times 256? 7 what? 68? Yeah, that's what I have, 68 too. Yeah. Okay. So let's subtract, and then I want to pause to show you something that's happening. Okay, so what do we get when we subtract this? 20. Okay. All the numbers that I'm getting along this right-hand side, right now I've got a 2, a 2, a 3, and I'm about to get something else here in a moment. All of those numbers have to be what numbers? What are my only options that could be? 0, 1, 2, and 3. Because I'm working in base 4. So if you get a number that's larger, you've got an error somewhere. Time to go back and figure out if you missed something, if you missed one of the numbers to divide by, or what happened. Because you should not be able to get a number that's larger than 3. All right. Now, I know this is going to look weird, but we are not going to skip any numbers. What came before the 256? 64. And I recognize this looks weird, but how many times does 64 go into 20? 0. But you need to represent it because you need to make sure you understand you have 0 of that number. It is a placeholder. Remember exactly the same problems that the Babylonians had? They didn't have that 0 placeholder. We don't want to have that problem. So you need to make sure it's present in there. It makes the subtraction easy because I still have 20 left over, right? And then what number will I divide by? 16. That one actually goes in one time. I'll subtract my 16, which leaves me with 4. What am I going to divide it by? 4, which goes in then once. I know I'm going to subtract, and I know that I'm going to get nothing, but I don't get to stop until I divide by the number 1. It is a placeholder issue, right? How many times will 1 go into 0? 0, right? But it's part of my solution. It's part of my answer. I have 0 ones. So my answer is right here. My answer is 2230110, and you must write base 4 next to it. Now, I want you to notice something. my earlier part of this slide. Can I get back up to the top? I don't know if I can or not. Now I can get to a different slide. Not what I was wanting for. Oh, well, that's fine. All right, my answer's down here a little bit further. You have yours written down. The number started out looking like a 5-digit number, and it was in base 10. When I turned it into a base 4 number, it ended up being a 7-digit number. So this always happens. When you change the base, a bigger looking base has a smaller valued digit in front. Okay? Base 10, I've got the number that's 11,000, right? Big base, small value in front. When the base became smaller, it is base 4, the number in front now looks larger, right? It's a give and take. If I change the fact that I've got fewer numerals, it takes more numerals to create the number. So that should always happen. It's a good check step at the end to say, does this make sense? Is it reasonable? Remember those problem solving things that we did before? This is one of those reasonable questions, okay? The other thing to make sure of, and we're going to do one more problem, but the other thing to make sure of is that you're multiplying and dividing appropriately. This is something I put on your note card to make sure that you don't multiply when you should be dividing and dividing when you should be multiplying, right? Because when I went from from their base, from a base 4 or base 10, 6 or base 2 or whatever, into our number system, what operation did we use? Multiplication. But when we go from our number system into somebody else's, we use division. All right, let's do one more of these. We've got the number 99,999, and it's in our base 10, and we're going to turn it into base 9, where there are no 9s, right? Okay, so the first thing we need to do is what? I need to write out the bases, the powers of 9, right? Okay, so the first power of 9 is actually 1 and then 9, and I'm happy with those. What comes next? 9 squared, which is 81. Then 9 cubed, which is 729, okay. How about 9 to the 4th? 561. Did I write that right? Okay. What's 9 to the 5th?
59,000.
Okay, and I know I can stop there because I'm at 59,000, the number's only 99,000. If you're not sure, you can always do one more, it's going to be much, much too large. So we're ready to set up what's called the division scaffolding. So the number that we're working with is 99,999. And the first thing I'll divide it by is the largest power of 9 that will go into it. In this case, it's 59,049. And it will go in how many times? Once. Yeah. So I subtract the 59,000 to 49. And what do I get?
40,900.
Perfect. Next step, what do I do? Good. I'll divide by my next power of 9, which was 561. How many times will that go into 40,950? All right, 6. What is 6 times 6561?
Oh wait, just kidding.
I think it's smaller than that.
39,366.
All right. Let's subtract. What do we get? Okay, good. So I've got 1584 left, and I'm now dividing by the number 729. How many times will 729 go into that? It is 2. So what is 2 times 729? 458? Okay. Subtract. 126. Dividing by 81. How many times will 81 go in there? Just once. Yep. Okay, subtract 81. What do I have? 45. Now I'm going to divide by what? 9. How many times will 9 go into 45? 5. 5 times 9 is 45. Don't stop too early. I know you've got a remainder of 0, but your last step is always to divide by the number 1. And how many times will 1 go in? 0. It doesn't always end up being 0 at the end. It just was in these two examples. So of course this is done. My answer was along the side. It started with a 1, I think, right? Yeah. 1, 6, 2, 1, 5, 0. I'm in base 9, so it needs to be written. And again, look at that number. Smaller base than I started with, and I have one more digit. It's a larger looking number. It took more numerals to make it than it did. It took 6 instead of 5. Any questions on that? I told you those two at the end were going to feel like they took longer, didn't they? Yeah. Okay. This happened last time. I don't need FaceTime up. I definitely don't need me.